Right. It's time we met the host of our show, or at the very least, the central topic. The molecule that causes so much trouble for us, and everyone, and for society in general. Um, if you're old enough, you remember the days we used to be able to buy a decongestant without having to show our ID. Um, the molecule in question, of course, is meth, or methamphetamine. It has the chemical formula C10H15N. So we now know, or we've had the background now to know, that methamphetamine contains 10 atoms of carbon, 15 atoms of hydrogen, and 1 atom of nitrogen in a molecule. However, if you did a quick internet search, my guess is meth would be the top if you type that in. But you'd also discover that there are lots of different molecules and substances out there that have those same 3 elements in that ratio. There's another aspect to what makes a molecule, and that's how those atoms go together. Here's a picture of how meth goes together, and right off the bat, I don't know if you can see them, but the hydrogen atoms are kind of weak here. This is a picture of the meth molecule, and the meth molecule is something we are going to examine in great detail. Alright, now hopefully you can see it. The black circles, or the greenish circles, I guess, really, these greenish circles here, represent a carbon atom. This blue is nitrogen, and I've used red because the white wasn't showing up. Traditionally, when we use a ball structure, hydrogen's white. But the red is hydrogen. These lines that you see here, they represent a covalent bond. So everywhere you see a line, you see a covalent bond. And remember, a covalent bond is a shared pair of electrons. Covalent bond is a shared pair of electrons. You'll notice that we have 2 lines right here. Line here, line there. That's because that those two carbons are joined by a double bond, or 2 shared pairs of electrons. I'm not sure if you can read my chicken scratch there, but there's your molecule. Meth is a classic example of a type of compound known as an organic compound, and is a great segue, or I wouldn't say segue, it necessitates us discussing organic chemistry. When a chemist says they're studying organic chemistry, it doesn't mean they're growing their chemicals without the use of pesticides. What organic chemistry is organic chemistry is the study of molecules that contain mostly carbon atoms. If you look at our structure here, you'll notice that we have mostly carbon, right? The backbone of our structure is made by these carbon atoms. Most of the substances we come in contact with in our daily lives, including ourselves, are made from molecules that have those long carbon backbones. We already saw that in our discussion of biochemistry that we did earlier. All right, let's get to the overhead we're supposed to be, where I actually have these definitions typed out. I get excited and I get ahead of myself here. Here's another picture of the meth molecule. Another pretty picture of the meth molecule. We'll look at it later. Let's keep going. Here we are. Organic chemistry is defined as the chemistry of hydrocarbons and their derivatives. Of the tens of millions of known chemical compounds, over 95% of the compounds are carbon-based. My definition I gave you on the other slide was better. Organic chemistry is the study of hydrocarbons. So what's a hydrocarbon? A hydrocarbon is the simplest the simplest organic compounds. As their name implies, they are composed entirely of carbon and hydrogen. In other words, organic chemistry is the study of compounds that are mainly carbon and hydrogen. Carbon is unique in its bonding, as we've already discussed in previous lectures. It's unique in its bonding in that carbon can bond to 4 other things. Because of its small size and its capability to bond 4 other things, it makes it a very useful, easy molecule to form strong bonds that are in close proximity to each other. And it's those factors that help contribute to it being the basis for all life as we know it and most of the things in the world around us. The simplest form of organic molecules are these hydrocarbons that consist entirely of carbon and hydrogen. Now, hydrocarbons can actually be divided up into a couple different groups. The first group of hydrocarbons, and the simplest type of group of hydrocarbons, are alkynes. Alkynes are hydrocarbons that contain only single bonds. Because all carbon-to-carbon bonds are single bonds, alkynes are often called saturated hydrocarbons. When we say something is saturated, remember back to our last discussion, when we say it's saturated, it contains the maximum number of hydrogens. As a general rule, a carbon can form 4 bonds, remember. Let's make a general rule for ourselves here. A carbon can form 4 bonds. So, in order to form larger hydrocarbons, what you have is you have carbons attaching in a chain to another carbon. Each of these carbons in the center have to use 2 of their bonds to keep the chain going. That means each of these carbons in the center can bond to only 2 hydrogens. Because they're bonding to 2 non-hydrogens, they only have room for 2 hydrogens. These terminal carbons can bond not only 2 hydrogens, but they can also bond 1 additional hydrogen because they don't have a rest of the molecule to go to. There's no rest of the molecule here. They're only using 1 of their 4 bonds to participate in the chain. So what you have is you have all these so when you have a hydrocarbon, all the carbons can bond at least 2 carbons. All the carbons can bond at least 2 hydrogens. Then the ones at the end can each bond 1 more hydrogen. So, what you will see is that for an alkene, we're talking alkanes or alkynes, both are acceptable pronunciation. For alkynes, the number of hydrogens is equal to 2 times the number of carbons, because each carbon can bond 2 hydrogen atoms, plus 2 hydrogens from the end. And that's the number of hydrogens that you'll find in an alkane. This even holds true if your molecule has branches. Let's take a look. I'm going to branch out with my molecule here. Do 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 do. All right, my molecule has developed some branches here. If I count my number of carbons, I've got 1. There we go. I like my red arrow better. 1, 2, 3, 4, 5, 6, 7, 8. So I have 8 carbons. So 8 times 2 plus 2 is 16 plus 2 is 18 hydrogens. That's how many hydrogens my hydrocarbon should have. Let's see if that's true. So let's add in our hydrogens now. I have this carbon right here. It's only participating in 1 bond, so it can take 3 hydrogens. This carbon is already participating in 4 bonds, so it can take no hydrogens. This carbon is only participating in 1 bond, so it can have 3 hydrogens. This carbon is participating in 2 bonds, so it can have 2 hydrogens. This carbon is participating in 1 bond, so it can have 3 hydrogens, right? We're going to give each carbon hydrogen until it has 4 bonds. This carbon has 1, 2, 3 bonds it's participating in, so to bring it up to 4, it can only bond with 1 hydrogen. This carbon has only 1 bond, so it can have 3 hydrogens. Same for this carbon, it's only 1 bond, so it can have 3 hydrogens. So let's see if adding branches changes that carbon-hydrogen ratio. Let's count them up. If our hypothesis about the ratio of carbons to hydrogen is correct, we should see 18 hydrogens here. So 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18. Nailed it! So, you can view it as a hard and fast rule that for an alkane, the chemical formula can be written C to the N to the H to the 2N plus 2, where N is your number of hydrogen, where N is the number of carbon. So if we wanted to test ourselves, if an alkane contained 12 carbons, how many hydrogens would it have? Well, our formula says that we take our number of carbons, we multiply by 2, and then we add 2. So 2 times 12 is 24, plus 2 is 26. So it would have 26 hydrogens. Chemistry is easy, life is hard. Life is especially hard if you're Ray, living alone, all alone in the galaxy, wondering when your parents are ever going to return. Everybody write down Ray, R-E-Y, Ray. Naming alkanes is also very easy. Alkanes all end in the suffix ane. Well, it doesn't do any help to suffix all end in the suffix. The alkanes all end in the suffix ane. What you do is you use a prefix or the first part of the name to denote the number of carbons. For example, if you have 1 carbon, it's methane. If you have 2 carbons, it's ethane. 3 carbons, propane. 4 carbons, butane. 5 pentane. 6 hexane. 7 heptane. 8 octane. 9 nonane. 10 decane. If this was a face-to-face class, I would tell you you needed to memorize those prefixes. As it is, I think you should just print out this slide, which hopefully you've done to take notes on, and have it handy when you're working your homework. For example, all right, let's name the 2 alkanes shown here in the picture. Black is carbon by convention. White is hydrogen by convention. So here we have 1 carbon that is connected to 4 hydrogens, meaning it has the maximum amount of hydrogens attached to it. So we use the prefix meth to mean 1, and the suffix ane to mean that it has the maximum number of hydrogens. Here we have 2 carbons, 2 black balls. Each of these carbons is involved in 4 bonds. Every bond not bonded to another carbon atom is bonded to a hydrogen. So this is an alkane as well, but because we have 2, we use the prefix eth. So this would be ethane. And these are simply space-filled models of the molecules up here, so we don't need to worry about those. All right, let's move on. What would be the name and formula of a compound with enough hydrogens to saturate the molecule? In other words, what would be the formula and name of a 4-carbon alkane? Well, remember that our number of hydrogens is equal to 2 times the number of carbons plus 2. So we have 4 carbons times 2 plus 2 is 10. So we have 10 hydrogens. So our formula would be 4 carbons and 10 hydrogens. Then, what would we call it? Well, we have an alkane with 4 carbons, so we use the prefix bute and the suffix ane, so it's butane, butane, which if you've been camping before, you recognize butane as what you take along to, that solid fuel you take along to burn. Let's keep moving. All right, pause me. Pause me and try this one. I'm serious, pause me. Did you pause me? Are you pausing me? I'm going to keep asking you if you're pausing me until you pause me, so you might as well pause me. Are you pausing me? I got more pause than an 8-legged dog. All right. Hopefully you paused me. So let's take a look. This time we have 8 carbons. So to get our number of hydrogens, we multiply our 8 carbons times 2, we add 2, and that gives us 16 plus 2 is 18 hydrogens. So the formula would be C8H18, and we call it, since it has 8, we use the prefix octo, and then because it's an alkane, we use the suffix ane. So it's octane, gasoline, or the primary component of gasoline. Gasoline is really a mixture of different hydrocarbons. Really, we've already looked at ball and stick models, but let's just review them real quickly again. In a ball and stick model, you use circles to represent atoms and sticks to represent bonds. So when we say we have a ball and stick model, this is what the ball and stick model would look like. By convention, carbon is black, and I can't write white on white here. By convention, hydrogen is white. Also, generally, based on convention, oxygen is usually red, and also keeping with convention, nitrogen is usually a light blue. But you'll see both oxygen and blue conventions vary. I mean, there's no IPAC rule for the color of atoms in ball and stick models, but that's generally what people follow. Then you have a space-filled model, and a space-filled model is the exact same. You use a ball to represent an atom. However, instead of using sticks to represent bonds, your atoms are simply grown together. Both of these molecules here are propane. However, in our space-filled molecule, see our 3 carbons, 1, 2, 3, they've all grown together. That's what we talk about when we talk about a space-filled model. And our hydrogens grow directly into the carbons that they're attached to, instead of being drawn with sticks. Personally, I'm a big believer in the ball and stick model as opposed to the space-filling model. Another way of representing alkanes is to use a condensed structural formula. In a condensed structural formula, what you're doing is you're simply listing the atoms in the order that implies their connectivity. For example, I'm saying that propane consists of this carbon attached to 3 hydrogens, and it's attached to this carbon, which is attached to 2 hydrogens, and it's attached to this carbon, which is attached to 3 hydrogens. So you're telling people the connectivity by writing out the structure, but you're not doing any balls, you're not doing any lines or anything. You're just listing them in order. Because otherwise, if we just wanted to write the structure of propane, just the formula of propane, we could go like that. By writing it this way, I'm telling you who's connected to whom. And that's referred to as condensed structural formulas. You'll often find that alkanes are present in a homologous series. And what we mean by a homologous series is that the only thing that's different between the alkanes is the number of carbons in the chain. All the hydrocarbons we've really been looking at have been a homologous series, where we just keep adding carbon and hydrogens and making the molecules longer and longer and longer. When you look at this homologous series, we can make a couple predictions on their properties based on the number of carbons. And I'm going to get ahead of myself if I don't move to the next slide. I know my good, they do have it here, because this is what I was wanting to talk about now. So we have a homologous series. We have a bunch of compounds. Let me draw your attention to our compounds over here. All these compounds are alkanes, and they're all straight, boring chains, but we can see a couple things. First, let's note our number of carbons increases as we go down the page. look what happens to some other properties as we go down the page and the number of carbons increases. As the number of carbons increases, the molecule becomes heavier. It's harder to lift something heavy, right? That means for a chemical, if it's heavier, it's harder to get it into the gas phase. And somewhere there was a P chemist getting very upset with my exclamation of that. It really has to do with some intermolecular forces, but that's beyond the scope of what I want to talk about today. But we can see that as the number of carbon increases, the boiling point of the compound increases. We can also see the same is true for the melting point. As the number of carbon increases, so does the melting point. We can also see that as the number of carbons increases, the density increases. So boiling point, melting point, and density all increase with an increasing number of carbons. Not only that, but as we increase the number of carbons, we go from being in the gas phase for methane through butane to being liquids for pentanes through tetradecane to even to 16 carbons. But once we get to 18 carbons, we go to being solids. So our phases become more dense, right? We go from gases to liquids to solids as our number of carbons increase. And that's due to intermolecular forces that we're not really going to talk about at this juncture in the class. Oh, that just summarizes, and I even made this slide in advance. That summarizes what I just said on the other side. Keep it handy when you do the homework. In addition to having those long chains of hydrocarbons and alkanes that exist in chains, you also have hydrocarbons that form rings. When they're in the ring state, they're referred to as cyclic hydrocarbons. They're hydrocarbons where the carbons form a circle as opposed to a line. When we have a cyclic hydrocarbon, we violate our CnH to the 2n plus 2 no longer applies for cyclic hydrocarbons. The reason that's a no for cyclic hydrocarbons can be easily seen when we look at propane. What we have is we have propane in the cycloform, so we're referring to it now not as propane, but as cyclopropane. Cyclopropane was made from linear propane, and that linear propane, give me a time to do some artwork here. Our linear propane had 3 carbons and 8 hydrogens. The 8 hydrogens with the blue outlines with the white center. In order to form this cycle, remember our carbons can only connect in 4 bonds. So in order to form the cycle, this carbon here had to lose one of its hydrogen, and this carbon here had to lose one of its hydrogens in order to bond with each other. So each of those carbons, the terminal carbons that usually have that extra hydrogen, had to give up that extra hydrogen in order to form the cycle. So for alkanes, the formula is simply going to be CnH2n. For example, for cyclopropane up here, you can see that we have 1, 2, 3 carbons and 1, 2, 3, 4, 5, 6 hydrogens. So for a cycloalkane, our formula is CnH2n, or we have 3 carbons, so we have 2 times that many hydrogen, 6 hydrogens. To name cyclohydrocarbons, we simply add the prefix hydro. In other words, if we have 6 carbons, 1, 2, 3, 4, 5, 6, and no double bonds, we would use the prefix hexane. We would use the prefix hexane because we have 6. Oh, sorry, we'd use the prefix hex because we have 6. Because we don't have any double bonds or triple bonds, we would use the suffix ane, and we contain the maximum number of hydrogens. But because we form a circle, we would add the prefix cyclo. So we have cyclohexane. Cyclohexane. And the formula for cyclohexane, remember, is simply going to be C6H12. If we had hexane, linear, the formula would be C6H14, because those terminal hydrogens would be back. So that word cyclo makes a difference of 2 hydrogens, and also plays a big difference in the structure. Right. It says, without referring to table 9.2, write the molecular formula and complete the structural formula for the condensed structure of heptane. So they're telling me I have heptane, and I don't care if you look at the table. Let's go ahead and look at the table. We have heptane, so that means we have 7 carbons, because hept means 7. If we have 7 carbons, then 2 times 7 plus 2 would be 16. So we would have C7H16 would be the formula for heptane. If we were to give the condensed structural formula for it, your terminals, and actually I'm going to scoot my paper over here. Rewind if you didn't get that down fast enough. Now you know why I'm not an English major. Remember, when writing the structural formula for a linear hydrocarbon, those terminal carbons have 3 hydrogens because they don't form that second bond that all the other carbons in the chain do. So I'm going to have my first carbon with 3 hydrogens. Then I'm going to have CH2, and I'm going to have 2 terminal carbons and 5 center carbons. So 4 total. Whoops, I messed up. I was so busy counting carbons, I forgot to count. And now I've totally lost count. 1, 2, 3, 4, 5, 6, and now I need my 7th carbon, and that 7th carbon is going to be a terminal carbon as well. So that's my condensed formula. Another way of writing this, to make it even more condensed, we could have our terminal carbons, CH3, CH3, but in between we can put a set of parentheses. We can put CH2, because this is the part that's repeating, and this CH2 repeats 5 times, right? So we could write it 5 down there. So we could say CH3, open parentheses, CH2 sub 5, close parentheses, CH3. That's another way of writing our heptane. Rather than having to give ourselves writer's cramp of repeating that all the time, we can just write it in parentheses and say, hey, we're repeating it 5 times. If we were to go really fancy and try to draw the molecule, we draw our carbon with lines denoting single bonds to each of those carbons, each of those hydrogens. Then this carbon would be attached to a hydrogen, 3, 4, 5, 6, 7. So I've done my 7 carbon chain. Now I just go in and I fill in and make sure everybody has 4 bonds, which means for my center party, everybody gets 2, except for my terminal carbon. When I come to that last carbon, it gets 3 hydrogens to make sure that it winds up with 4 bonds total. And that's all there is to this one. Yes, chemistry is easy, life is hard. Particularly if you're taken away from your family at a young age and forced to join the First Order's Stormtrooper Academy, like Finn was. They didn't even give the poor guy a name. But you're going to help that by writing down Finn. Everybody write down Finn. F-I-N-N. Everybody write down Finn. Alright, here's another good one. This time we're being asked to write the structural formula for cyclopentane. Write the structural formula for cyclopentane, in case that writing is a little too hard to read there. So cyclopentane. We know it's going to be cyclic, and then we see the prefix pent. When we have the prefix pent, that means we have 5 carbons. So we have 5 carbons in a ring. Because we see they're cyclo, we know they're in a ring. So 1, 2, 3, 4, 5. So we have 5 carbons, all forming single bonds with each other. And because they've each formed a single bond with 2 other carbons, that means they can only form 2 other bonds. So each one is going to be bonded to 2 hydrogens. We can also check and make sure that it matches our prediction. Remember, for a cycloalkane, the formula is CnH2n because it loses those 2 terminal carbons when the circle closes. When the circle closes, it loses those 2 terminal bonds. So, if we've done this right, we should have something with a formula of C5H10. So do we have 10 hydrogens? 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. We do. So we've done it right. Let's move on to another example. Same thing as last time, but this time we're doing it for cyclobutane. So we've got bute, which is 4. And we have cyclo, so we know it's a ring. So we've got 4 carbons in a ring. Each carbon's forming 2 single bonds with 2 other carbons. That means they each only have room for 2 hydrogens. So that's cyclobutane. And again, our formula is CnH2n for a cyclohydrocarbon. So it would be C4H8. Isn't that great? It ends in 8. All right, let's take a break from the pure hydrocarbons and look at a series of hydrocarbons known as aromatic hydrocarbons. Aromatic hydrocarbons are hydrocarbons that have what is known as a benzene ring. Benzene is a very unique organic compound. The best way to explain benzene and to talk about benzene is to take a look at cyclohexane. If I have cyclohexane, then I have a 6-member carbon ring. And on that 6-member carbon ring, I have 2 hydrogens attached to each one of my carbons. What the benzene molecule is the benzene molecule takes every other single bond and changes it into a double bond. In benzene, you take the hexane molecule and you replace every other single bond with a double bond. So we've got our cyclohexane over here, and what we're going to do is we're going to replace every other single bond with a double bond. So let's draw that skeleton again of cyclohexane. And we're going to give every other carbon a double bond. So starting randomly, and I'm just choosing to draw my first double bond here randomly. So I form a double bond here. I skip this one because I'm doing the double bonds every other single bond. So I draw my next double bond here, skip the bond, and draw my next double bond here. So that's benzene. Every other bond is a double bond. Then, how many hydrogens can each carbon have now? Well, in cyclohexane, each one could have 2, because each carbon was only participating in 2 carbon-carbon bonds. But in benzene, each carbon is now participating in 1, 2, 3 carbon-carbon bonds because of that double bond. 1, 2, 3. So each carbon is participating in 3 bonds. So each carbon can now only have 1 hydrogen. So we went from cyclohexane, C6H12, to benzene, C6 still, but because of those double bonds, we only have 6 hydrogens. Benzene gets even cooler. And here's why benzene gets even cooler. Let me clean things up just a little bit here. Remember how I said I chose the location of my first double bond in this molecule completely at random? After all, why did I choose to draw my first double bond here? as opposed to here? I mean, what would happen if I did that? Well, let's just take a quick look and draw another benzene molecule here. This time, I'm going to draw my first double bond here. That means I draw my second one there because I'm doing that skip pattern. Oh, that just got a little messy there. Now let's clean this up a little bit. So I've shifted the double bonds over one. That doesn't change my number of hydrogens, but it does change the location of those double bonds. So, which is the correct form of benzene? How does benzene actually exist? If I was to look at benzene under a high-power imaging or perform some tests, how would I see benzene actually existing? Turns out that because there's an equal probability of the double bond being here and a double bond being here, the molecule gets very confused. And those double bonds are continually shifting their location. In other words, at one moment the molecule has properties similar to this, and at one moment the molecule is similar to this. They shift so fast, in fact, that rather than try to draw benzene one of those two ways up there, benzene is instead represented as having that six-member carbon ring with a circle in the inside to show that you have a double bond rotating between all the carbons, that you have those three double bonds constantly shifting their location. Molecules where you have that shifting double bond feature, like you do in benzene, are said to have something known as resonance. We call it resonance because if you've ever hit a tuning fork, you know that tuning fork tongs resonate, right? We've looked at a tuning fork and we've seen those ends vibrating back and forth, vibrating back and forth, vibrating back and forth. That's how we as chemists kind of think of these molecules. We kind of think of the molecule of benzene as vibrating back and forth between these two forms. But because we give ourselves writer's cramp, trying to say that the molecule existed in a state between these two molecules, we simply draw it racetrack style with a circle in the middle. Not only that, but benzene is so important chemically, and the hydrogens are so unimportant chemically to benzene, that you'll often see benzene drawn using a stick notation. Drawn using what's known as stick notation. And you'll often see benzene just drawn as a six-sided object with a circle in the middle. And that's benzene. Now, benzene also has a high-class cousin, Mercedes benzene. Get it? Benzene, Mercedes benzene. Get it? Get it? That was funny. That was a joke. That was high chemistry humor. Hey, I'm the hit of the office parties. All right. So that's benzene. Benzene is really important because lots of other molecules, known as aromatic compounds, are built on a benzene skeleton. Remember that benzene has all these hydrogens, and they've said that those hydrogens are relatively boring? Well, what happens is in order to make bigger molecules, those hydrogens will get replaced. For example, to form a molecule known as phenol, we replace one of those hydrogens with an oxygen and another hydrogen. And we get a substance known as phenol. So you'll discover that benzene plays a big role, a big part in your biochemistry and chemistry at all, and chemistry in particular. So that's benzene, and it's referred to as an aromatic hydrocarbon because of that circle in the middle, because of that rotating pattern of double bonds. Compounds with that rotating pattern of double bonds are referred to as aromatic. And yes, they do indeed stink like crazy. They're the nastiest smelling things. Aromatic hydrocarbons here's a figure of your book for benzene. Once again, you can see the repeating pattern, the alternating patterns of double bonds that you have in benzene. And what they're trying to do with this figure over here is they're trying to imply that neither of these two structures really exist. Instead, you have a synthesis structure where you have the electrons in these double bonds continually moving between all the carbons. It's more of a communal situation than it is a single possession, or even one of those two structures existing. But I think at this level in particular, it's simply easy to think of it as these double bonds continually rotating between the carbons. As I said, there are lots of things we can make out of benzene. For example, toluene, where you replace one of the hydrogens on the benzene with a carbon and 3 hydrogens. Ethylbenzene, where you replace one of the hydrogens with 2 carbons. Naphthalene. Ooh. Naphthalene sees you. Naphthalene is actually 2 benzene rings attached together. Then you've got orthoxylene, and you can see here paraxylene. What you can see is all the things that we can do with that benzene molecule by removing a hydrogen and attaching things to it. Lots of other compounds can be based and built on this benzene background. This is an awesome place for us to stop. Before we stop, though, why don't you write down BB8? Everybody write down BB8. That's it. I hope you're writing down BB8.